Oh, damn. Okay, hold on a second. I got to get myself to the right place again. Setting this thing up, there's always problems. Give me 1 second. How do I get this thing? Here we go. Okay, we're talks about hallucinations in AI. And a quick overview here. We know that AI is a language model, and we know that there are problems in AI. For example, you'll have the thing where bleach infused casserole was created as a recipe for AI. And obviously, no one would want to make any kind of casserole that would have bleach infused and eat anything that was bleach infused. So we started to look at why were hallucinations and why were these errors occurring. So this talks about the results of our research of why these things were occurring. Now, you figure that when you're going to start any AI project, you've got to answer four basic questions. First one's obvious. Why are you doing what are you doing? What human behavior are we trying to mimic? Secondly, we have to decide what factors do we use that produce the desired human fact, and what factors does the human use to produce the response that he expects, and how much each factor is relevant to create that result. And finally, since computers don't really think like humans, how do we encode all this stuff as a mathematical formula? Oops, sorry about that. Made a mistake. Give me a second. I got to try again. Share. What are we sharing? What are we sharing? Wait, nope, that's not what I want. That's not what I want. Yes, that's what I want. And I want to be on screenshot. Give me 1 second here. We will get back to the beginning. All right, sorry about this. Hit the wrong button. Now, a quick review here. We will create what is called an artificial neural network. Why is it called an artificial neural network? Because the developers originally who started working in the area of AI said, let's mimic what the neural network of the human looks like. So we create an artificial neural network. On our right is a basic artificial neural network. It has an input. It has input data, input nodes, inter, intermediate nodes, and a result node. Now, neural networks are not always that's simple. On the left, we have a very complicated one. You'll see there are numerous input nodes connected to a whole slew of layers of intermediate nodes. We'll be talking about the neural networks, so we'll keep this in mind as we go along. Now, when we're working with artificial nodes, we end up using the idea of nodes we normalize the data to be between the values of 0 and 1, -1 and 1. We'll see why we chose the range in a few slides later. As you go from input nodes, you have the intermediate or sometimes called hidden nodes, and they have aggregate weights. Again, they will sum up all the input values they have, and again normalize the values between 1 and 0. Output nodes will predict the desired result or the result we find. Again, normalizing it and making a decision. -1 being it is a false or it's not, it's a negative response, one being a positive response. Now we have links that connect all of the various nodes together. And what we just said, we use the following equation, which we'll let you read there. And you'll see that as we go from layer to layer to layer in a sequential form. We don't jump ahead, we don't jump behind because we'll have trouble. But you'll notice that the values are a sum of the sum of the weighted values. That's weight times times the value of the input node of all the upstream input nodes. Now, you'll notice that I said, how come we're using ranges from -1 to 1? You'll recall that if you did any work in back propagation, the mathematical values are 0 to 1. 0, the mathematicians say, is false, and 1 is true. And they're asked the question in back propagation, we want to prove that whatever the input is, it's true or it's false. Now, solving, we'll see, solving, let's solve a neural network problem using the idea of zero is false and one is true. Now, I'm going to use a simple problem and we'll say, let's say you're a paramedic and you're going to determine if a victim is alive or dead. The inputs we're going to use are the victim's breathing, the victim has a heartbeat, the victim's wearing a hat, and the victim's wearing gloves. And the result we want to look for is the victim dead or alive. Clearly, you would say, wait a minute, what effect does wearing a hat or gloves have the way the victim's alive or dead? Problem is, when you're training a network, you don't know which of your facts help or either give you a positive or negative response, because that's the purpose of training. Find out how much any one fact influences the positive or negative response. So if we take the data, look at the data, we're able to create our neural network first, and we did a little work here. As a result of back propagation, we will find out that we have 4 input nodes right across the top. The weights of the links are in the middle, and we have the result being a dead or alive. Now notice that the weights of the right 2 nodes, which is wearing a hat and wearing gloves, are 0.5. Why? If they were positive, if it was a positive or true fact, it'd be 1. If it was a negative or negative fact, it's 0. Well, it's halfway between, and working through back propagation, it will actually create a weight of approximately 0.5 for those last 2 nodes. Now, if we look at the results in here after back propagation, we find out we have all these cases, and we did this as a complete vet. But notice the 4th case. We have 0 breathing. The guy's not breathing. The guy doesn't have a heartbeat, but he's wearing a hat and he's wearing gloves. And we say, wait a minute, he's alive. Why? You'll recall, if I go back to the neural network, you would have on the going from left to right, is he breathing? You have 0 times 1 gives you 0. Heartbeat, 0 times 1 is a 0. 1 times 0.5 is 0.5. And the wearing of gloves is 0.5. 1 times 0.5 is 0.5. 0.5 plus 0.5 equals 1. And we said 1 was a true statement. So yes, according to using back propagation, we would say the person is alive. That's a problem. Clearly, if that was found in the problem, you'd say the computer had a hallucination. The problem was we are incorrect in using the idea of back propagation. Now, let's use back propagation, but this time let's use the range with -1 being false and 1 being true. As we look at the weights, you'll see the weight for the right 2 are 1, and the weight on the second 2 are halfway between -1 and 1 or 0. So you have wearing a hat is 1 times 0, which is 0. Wearing gloves is 1 times 0 equals 0, using the same case we had before. And you'll have breathing is 0 and heartbeat is 0, and that's 1, and that ends up being, he's not alive. And that'll be shown in the next slide as we see the truth table there. Here you'll notice we did not discover a hallucination. Clearly, we cannot use traditional back propagation in this type of environment. It potentially will cause us to create an hallucination, or better known to the developers, an error in the program. Let's look at some others. We know that when we're creating a program, if we don't have the answers, we're going to turn to an expert, a domain specialist of some kind. And he's going to supply us with all the features or all the facts we need. He'll supply us with training data, and he will supply us with perhaps initial weight approximations that he thinks are correct. But again, this is constrained to what the expert can consciously articulate. Notice the word consciously. This is going to be important on the next slide. Let me ask you a question. When you see 2 friends walking towards you in a hallway, What clues do you use to identify each of the friends? Hint. According to Freud, we don't have photographic memories. Can you tell me exactly what you saw? Was it their hairstyle, their nose, the way they smile, the gait of their walk, the clothes they wear? Well, Freud points out to us that each human has a conscious and a subconscious mind. You use both the conscious and subconscious minds to identify which friends are in the hallway. But the conscious mind is not aware of the inputs or the use of data of the subconscious mind in the decision making process. So, the question I asked in the beginning is you don't know what clues you are using. Think about if you were the expert and you use a clue that's in your subconscious mind. You can't tell us or the developer that you happen to use this piece of data that you needed. Again, without that piece of data, you could again create a a hallucination or an error in the state. Now, another problem we have is you'll find many people who develop models will say, well, what you want to do is you want to divide up all these test cases you have into training cases and test cases. That's good. But so you run through training and then you run through testing. But the question is, when you find after you run through training and the test says there's a problem, is the problem in the data or is the problem one of the problems saw before in the way you corrected the neural network? Here is again an example. In case one, we're going to look for someone who has a common cold, and you'll see that if we train with lines 1 through 3, we say you have the cold. If you have a temperature of 100, you have the common cold. But then if we test, and then if we actually run, look what happens in line 4. We in line 4 the system fails because we did not find the cold at 101, which is wrong. Is the data wrong? Or is the model wrong? We have actually no way at this point of determining which is which. Now, in a similar way, if we took the data 3 through 5 and trained with that, we would say, oops, the data in line 1 is wrong because because we had the common code. We did not have the common code at 101, but we have the common code at 100. What's the problem? Well, we don't know because there's no way for us to determine which is causing us the problem. Now, if you look at this also brings up the point. Although you decide to divide your test cases into two groups, the training group and the test group, you want to make sure at the end of the day, all of your test cases give you the proper result at all times. You could see for some reason when you happen to choose the line 1 and line 4 as our training data, we'd say, well, okay, there's maybe a problem in the training data, but then again we say the real data always gives us an answer. Well, no, it may not. You have to be careful in this case. Finally, let's look at these things which we should be doing to avoid hallucinations. First, if we're using neural networks and back propagation to train the network, we have to make sure we use the range, much like we did in fuzzy logic, values from -1 to 1, or else we're going to have a zero case that represents irrelevance. And we need a zero case represents irrelevance, or we will be creating hallucinations. 2, we want to supplement expert knowledge with structured knowledge. If you remember our example of the bleach infused rice casserole, someone once asked me, why could that occur? Well, if you happen to be a European and you happen to decide you're going to make dinner, you would go on the way home from work. You would stop by the butcher, buy your hamburger. You would go to the bakery, buy your loaf of bread. You would go to the grocery store. You may go to the stand outside and buy your fruit, your vegetables. You'd go to a dry goods store to buy pasta and your cheese and you'd go to the vineyard and get your bottle of wine. The problem you have at this point is if someone said, well, in the United States, all these things are available to us in a all these things are available to us in a supermarket, they would say, okay, I will just say anything in the supermarket I can make into food. Well, you would forget soap powder and bleach are sold in food. Here, our expert, we jumped ahead without realizing we did not compensate for the fact that there are other things sold that we had not thought about. Three, any data that cannot be reconciled with the training model should be removed. This is very important. If you just say, well, all right, that was just an outlier, it may not be. It may indicate you are missing data or there's a fact that you need that you had not included. Now, when these anomalies occur, you must have accurate logs to help you determine what the root cause of any hallucination. This is important. You just can't say it's a hallucination. I'm not going to bother about it. And finally, most important, don't deploy any models until full data set accuracy is achieved. Even if one hallucination is caught, go look for the problem of how to solve it. I thank you for your attention, and I turn it back over to the